Good morning, dear students. Today we discuss another important effect which operate in organic molecules, namely steric effect. The term steric means stereo or space. So it is the spatial interaction due to spatial crowding of bulky groups in a molecule which affects their stability, properties and reactivity. It decreases stability as the bulky groups repel each other. It causes obstruction to attacking agents in certain reactions, that is known as steric hindrance. To understand steric effect, we have a simple example. Cis but2ene has got two geometrical isomers, cis and trans. In cis isomer, the two methyl groups which are bulky means big, occupying a lot of space. So the two methyl groups are very close, they are on the same side, so they are very close to each other, so they will repel each other strongly. Or we can say that the electron clouds of these two groups will overlap and that will create a lot of repulsion. Because of this, cis isomer is less stable, but in trans the two methyl groups are on the opposite side. One is over here and the other is on this side. So there is no steric crowding, steric repulsion in trans. Therefore, trans is more stable than cis. Okay, so steric effect has a lot of applications. We take a few applications. One is in explaining stability of isomers, another one acidity and basicity, and then reactivity. The first application in predicting stability of isomers, the first example is the same one we discussed previously, the cis and trans isomer. Between cis and trans isomers of but2ene, trans is more stable because the two methyl groups are on opposite sides. There is no steric repulsion, but in cis isomer they are very close and there will be strong repulsion between the methyl groups. It is less stable. Now coming to the next example, that is conformational isomers of butane. In stereochemistry, you might have learned about conformational isomerism due to free rotation about carbon-carbon single bond. Butane, when drawn in Newman projection, suppose you are starting with this isomer that is fully eclipsed, where the two methyl groups are close to each other. So there will be strong repulsion between these two methyl groups which are close by. See, this steric effect is a non-bonding interaction, which means the two bulky groups which are interacting in space are not bonded to each other. Okay, so this fully eclipsed isomer is least stable. Generally, you draw four main conformational isomers for butane. When you rotate one of the carbon, you get the next conformational isomer, that is called gauche, where the two methyl groups will have a dihedral angle of 60 degrees. When you rotate further, you get another eclipsed isomer. On further rotation, you get this isomer, which is called fully staggered or anti. In the sense, the two methyl groups are on opposite side. There is no steric repulsion here. So this isomer is most stable among the four conformational isomers of butane. That is also explained on the basis of steric effect. Now we consider how we predict basicity of amines. Amines are basic due to the presence of lone pair on nitrogen, which they can donate. Amines are of different types, primary, secondary and tertiary. You can see in this order of basicity, tertiary amine is least basic. We have taken here methylamine, dimethylamine and trimethylamine. Methyl groups have got plus I effect, electron pumping effect, which always increase basicity. When there are more methyl groups, basicity tends to increase. So we expect basicity to increase from primary to secondary to tertiary. You can see here the basicity order is okay from primary to secondary. Basicity increases, but tertiary falls behind. Tertiary amine has got unexpectedly lower basicity in spite of having 3 plus I groups. There are 3 plus I methyl groups, but basicity is less than even primary. How do we explain this? This is explained on the basis of steric effect. In tertiary amine, there is a lot of steric crowding due to the bulky methyl groups. So it is difficult for nitrogen to donate its lone pair, because to donate the lone pairs H plus, the acid has to come and accept. So the approach of H plus is hindered sterically, which reduces basicity of tertiary amine. Another reason is, see, when a base accepts H plus, it becomes what is called conjugate acid. So this CH3 thrice N, when accept H plus, it will become CH3 thrice NH plus, which is a conjugate acid. Now there is no more lone pair. It is used for bonding with H plus. Now this conjugate acid will undergo solvation in the solvent, but this solvation is also sterically hindered. Approach of solvent molecules also become difficult, and that also reduces basicity, because you know that a general concept is that basicity of a base depends on the stability of the conjugate acid. Stabler the conjugate acid, stronger the base. Okay, so any factor which stabilizes the conjugate acid will make the corresponding base stronger. So here this conjugate acid of the tertiary amine find it difficult for solvation due to the steric crowding of the 3 methyl groups. So stabilization due to solvation effect is also reduced due to steric effect. These two factors make tertiary amine less basic than expected. It is least basic here in this order. Now coming to acidity, we consider carboxylic acid. You can see 2 examples here. One is benzoic acid, the other is 2,6-di-tertiary butyl benzoic acid, which is more acidic. Benzoic acid is more acidic. You can see the pK values. When 2 bulky tertiary butyl groups are placed at the ortho positions, there is steric crowding. So the proton donation becomes difficult, and subsequent solvation of the conjugate base also become difficult. So 2,6-di-tertiary butyl benzoic acid is found to be less acidic than benzoic acid due to steric effect. Now we have reactivity. We consider 2 examples here. One is the SN2 reactivity of alkyl halides. You know that the SN2 in SN2 mechanism, it is direct attack of the nucleophile on the carbon, and it expels the leaving group. The SN2 reactivity decreases from primary halide to tertiary halide, or tertiary halide is least reactive towards SN2 mechanism, SN2 reactivity. Why? You can see down in tertiary halide, there will be definitely 3 alkyl groups which are bulky. So the attack of the nucleophile become difficult. It is sterically hindered. That is why the reactivity is least for tertiary halide, and it is most for primary halide because their steric crowding is less. That is why tertiary halide opt another mechanistic path that is called SN1 mechanism. Now the next example is rate of esterification of carboxylic acid. Let me consider 2 examples. The first one is benzoic acid. See, during esterification, carboxylic acid react with alcohol forming ester. In the reaction mechanism, it is the alcohol which attack the carbonyl carbon of the carboxylic acid. So between benzoic acid and down you can see this compound, that is 2,4,6 trimethyl benzoic acid, which is having more reactivity towards esterification. Benzoic acid is more reactive. Then why 2,4,6 trimethyl benzoic acid is less reactive? Because of the 2 methyl groups coming in the ortho position, the approach of alcohol to these COH groups becomes sterically hindered. So steric effect reduces the reactivity. Practically there is no esterification taking place under normal conditions due to this steric obstruction or steric hindrance. In the second example down, if you take acetic acid, propanoic acid, or you can say it is propionic acid, similarly 2-methyl propanoic acid, 2,2-dimethyl propanoic acid, etc., where branching increases or steric crowding increases near the carboxylic group, what happens to the rate of esterification? It decreases. Here most reactive is found to be acetic acid, where there is no steric crowding near carboxylic carbon, and tertiary butyl carboxylic acid is least reactive because there is maximum steric crowding near carboxylic carbon. So these are various applications of steric effect. So it has a lot of applications, a lot of significance with regard to stability, reactivity, acidity, basicity of organic molecules. Okay, with this we come to end of this discussion. Thank you.